This is Chemistry 111, Unit 4, Part 3, and this is the last chapter in the course, Properties of Liquids and Solids. So we've been building up to this chapter basically ever since we stopped studying gases at the beginning of Unit 3, and we talked about thermodynamics and energy, and then we started at the atomic level talking about electronic structure, and then building up to the molecular level looking at molecular structure. And now, once we understand all of that, we can put all these pieces together and actually understand both the liquid and solid state of matter. So, both liquids and solids are condensed phases of matter, meaning that the particles are close together and that they interact, meaning they have potential energy. And so, we've talked about potential energy quite a bit leading up to this, and part A here, this is the potential energy within chemical bonds. And again, we've been talking about that throughout. And so when we break chemical bonds and form new chemical bonds, that means we have a chemical reaction taking place. And as a matter of fact, for gas phase reactions, we can estimate the delta H by figuring out the bond energies as we did in a couple chapters ago. However, in this chapter, we want to understand the other type of potential energy in chemical substances, and that is what is called intermolecular forces. We sometimes abbreviate this as IMF for intermolecular forces. And in molecular compounds, these are the forces that hold the molecules together. So we're talking about molecule A to molecule B. So we've got a molecule of compound A here, we've got another molecule of compound A here. We sometimes show these with dotted lines. So this attractive force in between the two molecules would be an intermolecular force. And so once we understand these intermolecular forces, then that's going to help us predict pretty much all of the properties and understand how these materials behave and interact with other materials. So there are basically four main types of intermolecular forces that you'll see within pure substances. And then when you expand this out to mixtures, there are another 3 different types of intermolecular forces. So there are 7 different types total. Let's start with the first 4 that you'll see in pure substances or mixtures. So you can see any of the 7 in a mixture. You can see these first 4 in pure substances. So the first is called a dispersion force. This force actually has a lot of different names, partly because scientists basically figured out that this force had to exist even though they didn't really know what it was or where it came from. And so early chemists had lots of different names for this. But the best name, in my opinion, is dispersion forces. Some people call it London forces. Some people even combine those terms, London dispersion forces. The word van der Waals forces is an older term that some particularly organic chemists still use. And then later on, you're going to see a lot of these forces are named based on the types of particles that are interacting. And so sometimes these are called induced dipole forces. Again, all of these terms are interchangeable. They all mean the same thing. These are the weakest forces within particles, and they occur between all molecules, ions, or particles. So we can even be more general with that statement. However, in nonpolar substances, this is the only force present. It increases with the size of the molecule with molar mass. So for example, if I drew out 2 molecules of CO2, CO2 is a nonpolar material. And basically you can think of this entire molecule as having one big electron cloud. And as the electrons in this molecule are moving around, they sort of shift or slosh back and forth, kind of like water in a bathtub. The bigger the bathtub, the bigger the container full of water, the more it's going to sort of slosh around. You can sort of think of the electron cloud like a water balloon, so to speak. And on average, the water, or the electrons in this case, is not sort of sloshed towards any one side over any other, but at any given instant, it could be. And so, at any given instant, if the electrons are shifted further to the right than they are to the left, this will create a temporary induced dipole. And if there's a slight negative charge here, that's going to shove these electrons away, creating a slight positive here and a slight negative here. And so one molecule induces a dipole onto the next. But over time, the electrons are constantly moving around. So in the next instant, it could all be backwards of what I've just drawn on the board. Again, the key thing is temporary. These are not permanent dipoles. So you can imagine if I had a larger molecule like CS2, where the sulfurs are bigger than the oxygens, now you've got essentially a bigger electron cloud, bigger water balloon, and so the electrons are going to move around even more. This tendency of electrons to sort of slosh around within the electron cloud has an official name. It's called polarizability. And this is an ability of an electron cloud to deform, causing these temporary dipoles, these temporary uneven shifts of electron density. The second type of intermolecular force is called a dipole force. This is a stronger force than dispersion forces. And the classic example here is formaldehyde. Formaldehyde has a permanent dipole with the oxygen end being partially negative and the carbon-hydrogen end being partially positive. If I draw a second molecule of formaldehyde, I now have a partial negative and a partial positive again. You will get an attractive force. This dotted line I just drew here represents the dipole force. And it's the same concept as dispersion force, except the dipoles are permanent now. They're not constantly changing and moving around and switching back and forth. We have a permanent positive end and a permanent negative end, and they attract to the other molecules in the substance. The third type is called a hydrogen bond. Now notice I have bonds in quotes there because, again, we already talked at the beginning of this section about the difference between a chemical bond and an intermolecular force. Hydrogen bonds are intermolecular forces, not bonds, and so I, again, use the word bond here in quotes. I wish that we hadn't named this force this. I wish we'd have come up with a different term. I wish we would have called them hydrogen forces or hydrogen interactions or something. But in any case, this is an unusually strong special type of dipole force. It occurs in it occurs between any two molecules that have a hydrogen that is connected to H, O, or F. Or excuse me, N, O, or F. Excuse me, I said that wrong. But notice the hydrogen in each of these is attached to one of those three. Now notice that I just put the compound HF in there. Both hydrogen and fluorine only form one bond. So the only molecule the only time hydrogen is connected to fluorine and is eligible for hydrogen bonding is in that compound. When we talk about mixtures in a few minutes, you're going to see that this is actually a little bit more liberal the way we define it when we get into mixtures. But in pure substances, you have to have an NH, an OH, or the compound HF in order to see hydrogen bonding. And so the classic example is water. Water has this bent shape, which creates a permanent dipole. And so the next water molecule comes up here, has also its partially positive and partially negative end. And so I'll try to use a different color this time. I probably should have been doing that without. But here in red, this dotted line would represent, in this case, a hydrogen bond. Now again, a hydrogen bond doesn't look any different on paper from a dipole force. It just happens to be that this H and this O are part of that criteria that allows this to be a hydrogen bond. And so for whatever reason, that dotted red line I just drew is a stronger force than the dipole force that we drew in formaldehyde. Now notice in formaldehyde has H and O, but they're not connected to each other in the molecule. In formaldehyde, the C is connected to the H, and the C is connected to the O. And so the dipole forces that form are not considered hydrogen bonds. They're weaker. The fourth type of intermolecular force is called ionic bonding. And again, you see that word bond again, and you might think, wait, I thought we were studying intermolecular forces. But remember, if you go back to the very beginning here, it says in molecular compounds, we will have this second type. So if you go all the way back up here to intermolecular forces, notice in molecular compounds, these are the forces that hold molecules together. Well, the problem with ionic compounds is we don't have molecules. And so there is no distinction between bonding and intermolecular forces. There is only one type of potential energy in an ionic compound. And so we have to discuss ionic bonding as both a chemical force and a physical force because it's the only force that's there, and so it determines all of the properties, both chemical and physical. Ionic bonding is much stronger than the intermolecular forces we see in molecular compounds. So these are going to be again, much stronger. Again, if we come down here, this is not really an intermolecular force by our definition, but that's the only force we have to talk about when we're dealing with an ionic compound. Now, there are three other types of intermolecular forces that can exist. You will only see these, however, in mixtures. And they'll be in mixtures where you have different types of particles interacting. When you have an ionic compound mixing with a polar or a nonpolar, or if you have a polar mixing with a nonpolar, then you will get these three combinations. And these are just named based on the types of particles that are interacting, so you'll see a little pattern here. The most common of these is when we do dissolve an ionic compound in water. You will get what's called an ion dipole force. And so if you dissolve sodium chloride, if we go all the way back to Unit 2 for a second, and we draw our beaker picture of salt water here. If I draw a water molecule, again, as we saw, water has a partially negative end. I'll switch back to blue here. This dotted blue line between the positive sodium and the negative oxygen is called an ion dipole force. And again, why do we call it that? Well, sodium is an ion and water is a polar molecule, so it forms a dipole. And so it's an interaction between those two things. Similarly, if I draw a water molecule surrounding the chloride ion, then my dotted blue line will be between the hydrogen and the chloride, because the hydrogen is going to be a partially positive end of that molecule. And so again, opposites will line up here. And so those blue lines are ion dipole forces. Those are the most common of the mixture intermolecular forces. You will occasionally see others. An ion-induced dipole force would be between an ion and a nonpolar molecule. So for example, if you had like a soda, for example, a soda or a pop, whatever you want to call it, if you had a carbonated drink that also had salt in it, the CO2 is a nonpolar molecule, and then you have your salt in it as well. If the sodium ion and the CO2 molecule were to come into interaction, this would be an ion-induced dipole force. The positive charge from the sodium would attract the electrons from the CO2 toward the positive charge, which would induce a dipole on the CO2. Remember, CO2 is nonpolar, so this is what we call an induced dipole. It's the positive charge of the sodium that is forcing the CO2 to become at least temporarily polar as those two molecules interact, or as those two particles interact. And then the final example would be a dipole-induced dipole force. And this is between a polar molecule and a nonpolar molecule. So again, going back to our carbonated beverage example here, CO2, which is nonpolar, dissolved in water, which is polar. And so if a CO2 molecule interacts with the hydrogen end of a water molecule, that will do the same thing that we saw in the previous example. The electrons from the CO2 will be pulled towards the positively charged hydrogen, which will induce a positive dipole on the other side. And so that's a dipole-induced dipole, polar-nonpolar. The next segment of the video will go over the problems on the next page. Try to think about the different types of intermolecular forces and see if you can apply them to each of the different situations.